my intuition is that in order to understand quantum mechanics, you have to understand that we live in a complex world, but are only able to perceive real things. And that particles can visit the complex world and come back out into the real world and so on. But I don't know, I can't give you a serious answer about how to approach this problem. Okay, I don't know enough. And I mean, it's a really, really hard question, and I wouldn't even begin to fake it.
In the following conversation, I speak with one of the world's most creative and renowned applied mathematicians, Carl Bender from Washington University. Carl was also one of my own favorite lecturers. I invited him on the podcast because he has a unique talent for making complicated mathematical ideas not just understandable, but conceptually beautiful. In the following, we discuss the history of imaginary numbers and how they fit in with reality. We also discuss Carl's interactions with Richard Feynman and his own research in quantum mechanics. I'm Shane Farnsworth, and this is the Escape Sapiens podcast, supported by the Andrea von Braun Foundation. If you value this content, you can have a direct impact on its success by liking, subscribing, and sharing. And now, here's Carl Bender. I hope you enjoy.
Escape Sapiens.
So let's start with some philosophy of mathematics. Is the effectiveness of mathematics in describing the natural world, in some sense, unreasonable or mysterious?
Now, that's an interesting question. Mathematics is a subject in itself. You know, it's a contained subject. It's internally self-consistent, or not. Okay. The question is, can it be applied to describe the real world? And that's a very interesting question, because it isn't obvious that mathematics has anything whatsoever to do with the real world. And it's an extraordinarily amazing thing that it does. And the recognition that mathematics, in some sense, describes what's going on in the real world, that took centuries for people to become aware of that, right? I mean, orbital mechanics is a typical example. You know, when you can predict the positions of the planets, or you can predict an eclipse, that's extraordinary, because there's no obvious reason why nature should obey any kind of mathematical formula. So, yes, that's a deep question. Why should mathematics have anything whatsoever to do with reality as we perceive it? Okay. And of course, in a dream, if you can distinguish reality from a dream, but in a dream, you look around and things are happening without cause, and they do things that are unpredictable. You know, you could be floating in the air, you could be whizzing through the air, and so on. And mathematically, there's absolutely no possible way to explain that. So what's the difference between dream and reality? Is reality is mathematics an essential description of reality? I don't know. It appears to be, of course, and people have been able to predict mathematical consequences and observe them in reality with incredible precision. Okay, so, you know, the bottom line is that mathematics appears to be a complete and total description of what happens in the real world, but I have no idea why.
But do you think that
I don't have a deep explanation of why, right? I mean, I can walk into the laboratory and show you experiment after experiment where I make a prediction about what's going to happen and measure it with great precision, and what I predicted really happens. Okay, but I can't give you a deep reason why it should.
Do you think there might come a day where we hit a limit? So for example, at the moment, we're trying to reconcile quantum mechanics with gravity, right? And that's the biggest, I suppose, most difficult question that physicists are currently working with. And
Right.
here I'm thinking along the line of Gödel's theorem or something like this. Do you think there's going to come a time when really everything breaks down and we can't go any further?
Actually, yes, I do. Yes, I do. There are now amazing experiments where you can measure extraordinarily short times, phenomena happening on extraordinarily short times. But if it happens on a short enough time, then quantum mechanics comes into play. And, if we're talking about times of order 10 to the minus 20 seconds, how does a particle move over a time scale that short? And it isn't at all clear. That is, if you're making measurements of a millionth of a second, now you're still talking about motion on the distance scale, say, of a bacterium or something. Mm-hmm. But when you're talking about 10 to the minus 6. But when you get down to 10 to the minus 20, the uncertainty principle comes into play. It's not at all clear what is happening. It may actually look like a fantasy world on that kind of a time scale. So you ask, will mathematics continue to apply forever? I have my doubts. At very, very short time scales, things may just look like a soup and they may be undescribable. Okay, that's a very interesting question.
Do you think perhaps in those cases, it could be the case that we just need a different set of axioms? Mathematics doesn't break down, but that we're just using the wrong axioms, but potentially.
I have no idea. I mean, it could be that in extreme physical cases, the current theories of physics, how physics works, may no longer be valid. And it's conceivable that there's a new physics that happens at a microscopic level, very, very short times, very short space distances. But maybe it just is sort of looking at a bowl of Jell-O, and that what we're seeing is in some sense an average of all of these microscopic things all happening together. Okay. That could be. That could be. It's not at all. I wouldn't even guess what's going to happen as you make finer and finer measurements. But that's a really good question. I just have absolutely no idea. I don't even know whether I should formulate an opinion because it's not based on anything. Okay. But it is clear that there are many things that happen, and already it's very hard to describe the process. When a particle tunnels, what is happening while it's tunneling? Where is the particle? Okay. And, you make up a word if you're a physicist to cover up the fact that you don't understand. Okay.
Like dark matter or dark energy.
Or that's right. And in this case, when a particle is tunneling, you call it a virtual particle. But that doesn't explain anything. It's just a word. Okay. And so the question is, how does, if there's a potential hill, okay, the particle strikes the hill, classically it would bounce back. Quantum mechanically, every once in a while, the particle goes through whatever that means and reappears on the other side and keeps going.
But then here it seems like this is not a case that fits what we're talking about exactly, right? Because we can predict to extraordinarily high precision the tunneling rate, for instance. So that right. Seems to be something that does fit within the realms of what mathematics can describe.
That's right. That's a quantity that you can calculate, such as, the tunneling time. However, you cannot predict whether or not a given particle is going to tunnel. And if it does, while it's tunneling, so we have this vision of continuity. We live in a world where things are continuous. So if I throw a baseball, that baseball is always visible to me. Okay. And it's moving in a continuous way through a medium. Okay. But when a particle tunnels, you can't say where the particle is as it's tunneling. So I lose sight of the particle on one side of a potential hill. And then I see it again on the other side. And I don't even know if it's the same particle. If it's an elementary particle, if an electron strikes a potential barrier and an electron comes out the other side, is it the same? Or is it a different electron? And where was the electron as it went from one side to the other? Okay, and so we have this in our world, we see things happening continuously. We don't pick up a rock and throw it. It disappears from view and then it reappears, 10 feet later. It doesn't do that. But in quantum mechanics, it seems to. Okay, now I would argue that that tunneling object, that tunneling particle, is actually going through the complex plane. But that may just be a mathematical description of this tunneling phenomenon. Okay.
This might be a good point, I think, to jump in, because the complex numbers are going to be appearing throughout the discussion. It might be a good opportunity to introduce them. For the person who has no physics background, no mathematics background, are you able to describe, I can remind you of the list, but what are imaginary numbers? What are complex numbers? And how do we first come up with them?
Right. So when numbers were first invented, that is, you were counting your toes or counting your fingers, it's clear that even some animals understand small integers, 1, 2, 3, 4. Okay. But it eventually became clear that there were other numbers, because you could add 1 and 1 and get another number. But if you subtracted 1 from 1, you got a new number, which was 0. And it took a while to absorb the fact that 0 is also a number. Okay, but we're not done yet, because although there's no problem with addition now, if you start with one number and add it to another number, you get a third number, no problem. 1 plus 2 equals 3, and 3 is a positive integer. But now subtraction gives us a problem. Okay, because 2 minus 1 is 1, and that's fine. But 1 minus 2, what do we mean by that? Okay, and so we need to append the negative integers just because we understand that we can subtract as well as add. Okay, I can give something away as well as taking something in. Okay, now multiplication is fine. Also, I can multiply. I can say 2 sets of 5 is 10. But division, again, gives me a problem. So just the way the inverse of addition, which is subtraction, gave me a problem, the inverse of multiplication, which is division, leads to a new problem. Okay, what is 2 divided by 3? And that's no longer a number. And I'm forced to append the rational numbers. Okay, so every time I have a new mathematical operation, I may have to extend the number system. And this is worrying because I may think of an operation and then have to make the number system bigger and bigger and bigger. So for example, the operation of taking a square root. Okay. So if I take the square root of 4, I get 2. And if I take the square root of 9, I get 3. But if I take the square root of 2, it isn't a fraction. It isn't a rational number. Okay, so I have to append a new set of numbers called irrational numbers. And then, of course, I can take other roots. I can take third cube roots, fourth roots, fifth roots, and so on. And these, fortunately, don't generate new kinds of numbers. But we have both rational numbers, and now we have irrational numbers, and eventually we have transcendental numbers. Okay, these are new kinds of irrational numbers, like pi. Okay, but we're not done yet. And this is the really interesting case. One kind of mathematical operation is to solve an equation. So I can write down an equation like x squared equals 1. And I can say, what's x? And the solution is either +1 or -1. And you come to realize that if you have an equation that contains a square, there are 2 answers, which might happen to be the same. But they're not more than 2. And if I have a cubic equation, there are 3 answers. But so I have a new mathematical operation called solving an equation. But what about the equation x squared equals -1? Okay, so what number, when you square it, gives -1? And it was recognized very early that there must, either we can't write down that equation, or if we want to be able to solve the equation, we have to invent a new number. And this is a very strange number, and it's called I for imaginary. Okay, and I is a number, by definition, whose property is, as one property, that I squared is -1. And so I can solve the equation x squared equals -1 by inventing one new number, just one. Okay. And now we have to, it took a long time to agree that I is a number, because it doesn't look like other numbers. Okay, it's imaginary. But it was accepted after a while. But the first, and it was recognized that when you write down a quadratic equation, like x squared equals -1, a root can be imaginary. Okay, or it can be complex. That is, it can be a combination of a real number like 3 and an imaginary number like, say, 6i. Okay, so that we'll call that a complex number. Okay, but now we're not done, because now a miracle happens. Okay, this was back in the 1500s, somewhere around 1535 or 1540. So imaginary numbers were already being accepted. Okay, but Cardano realized that you could have, you could write down a cubic equation, and once again, not all the roots of a cubic algebraic equation can be, it's not obvious whether or not those roots that are not real are also complex, in the sense that those roots are combinations of a real number and an imaginary number. They may require a new number yet. And the miracle is they don't. And that's an amazing fact. Okay, it's amazing. Now, he was very interested in cubic equations, and he spent his life thinking about it, many, many years. And he understood it. He came up with a cubic formula, like the quadratic formula that you learn in high school. And then later on, shortly thereafter, it became clear that higher degree equations like quartic equations and so on don't require new numbers. In other words, it appears as if you have filled out the number system and there aren't any ways of generating new kinds of numbers. Okay, now there are new kinds of mathematical systems. Okay, there are systems of matrices and so on. But in terms of numbers, just numbers, and I'll say what I mean by that in a second. But these numbers are now complete. Mm-hmm. But the real numbers, which includes the positive numbers, the negative numbers, the rational and irrational numbers, and then those real numbers multiplied by I together. So A plus I times B, where A and B are real numbers, those numbers fill out the complex number system. And it's remarkable that there aren't any operations that force us to bring in new kinds of numbers. There are new kinds of number systems that exist with even more advanced kinds of numbers belonging to those systems. But this system is complete. And this is a beautiful, beautiful result. And the complex number system needs to be there. Okay, it has to be there because what is happening in the system of complex numbers is connected to what is happening just for the real numbers. We would say on the real axis. So the real numbers are on a number line, a one-dimensional number line. The complex numbers lie in a plane. This is the imaginary direction, the I direction. This is the real direction, okay? And any point in the plane has the form A plus I times B. A is how far you are in this direction. B is how far you are in the imaginary direction, and you multiply that by I to keep track of that. So A plus IB is a point in the complex plane. In order to understand what is happening with the real numbers, you need to know what is happening in the complex plane. There are all kinds of phenomena that cannot be simply described just in terms of real numbers. And that's remarkable.
Could you give an intuitive picture of how these are actually used in engineering and science? So what sort of scenarios arise where you might need them?
Well, first of all, in mathematics. Okay. So if you take the function 1 over 1 plus x squared, okay, 1 divided by 1 plus x squared. If you plot that function, it is a very smooth function on the real axis. So a kid in junior high school can make a plot of the function 1 over 1 plus x squared. The plot looks like this. It has a nice smooth bump in the middle. It falls off to 0 as you go off to infinity. Couldn't be smoother. Okay? And if you know calculus, this function can be infinitely differentiated. So it can be differentiated an infinite number of times. It has no discontinuities. It is perfectly smooth. However, if you expand this function in a series, just by expanding it in a geometric series, 1 over 1 plus x squared is equal to 1 minus x squared plus x to the 4th minus x to the 6th, and so on. that series diverges if x is bigger than is one or more. Why? Why does the series diverge? Why is it that
is it 1 over 1 minus x squared, or
no? What that has a place where it's infinite. Okay, 1 over 1 minus x squared becomes infinite when x is plus or minus 1. So you could say, oh, I know why the series for that function diverges, is because the function becomes infinite. Okay, so the series for that function converges until the function becomes infinite. Okay, I can buy that. But what about 1 over 1 plus x squared? That function is perfectly smooth. It doesn't ever become infinite. And yet, the series that represents that function ceases to converge. It becomes infinite when x equals 1 or when x equals minus 1. Why is that? And the answer is that there are places where that function does become infinite, but not on the real axis. It becomes infinite in the complex plane. And in the complex plane, it becomes infinite at x equals I, at x equals minus I, and that's because I squared is minus 1. So 1 over 1 plus x squared becomes 1 over 0. And so it blows up. So the function becomes singular, that means infinite, in the complex plane. But the fact that it is infinite in the complex plane 1 unit away from the origin in the vertical direction apparently affects what is happening 1 unit away in the horizontal direction. That is incredible. So what is happening on the real axis is controlled by what is happening in the complex plane. So there's a connection. So we live on the real axis. Everything that we perceive is real. When you look in your wallet, you have a real number of dollars. Okay? When you measure your IQ, it's real. Okay? When you measure a quantity of anything, you count it in terms of real numbers. And indeed, if you ask how many, spoonfuls are there in this container here, it may be a rational number, but it's a real rational number. Okay, but the complex numbers do affect how the real numbers behave and how operations on the real numbers are performed and how effective they are. Okay, so when you represent a function by a series, that series may cease to converge, and when it does, the explanation has to do with what's going on in the complex plane. Okay, and there are interesting physical examples of how the complex plane is affecting the physical behavior of objects. Okay, so that's quite subtle and quite interesting, and we can see it even in elementary. We don't have to go to quantum mechanics to see problems like this. We can see it. We can see it in the case of classical mechanics, just simple classical motion. We can see things that are happening that are very hard to explain with real numbers alone. But there are also real problems that we cannot understand without using complex numbers.
So if a student who was just learning about imaginary numbers came to you and asked, are these things real, or are they just a mathematical trick? I suppose then your answer would be, we can measure it, right? We can go ahead and there are functions that we can calculate, and they behave the way they do only because of the existence of the imaginary numbers, and their behavior can only be explained by the existence of the complex numbers. So in that sense, there is real as real numbers. There is measurable as real numbers.
Right. So we can imagine, this is just a simple classical mechanics problem. Okay. We can imagine a hill like this. We can balance a ball on top of the hill. Okay. And the ball may, if it's perfectly balanced, classical mechanics says that it will stay there. But we call it unstable because if you give it a push, even with a feather, it will begin rolling down the hill. And if we have a hill that's going continuously down, the ball will roll going faster and faster and faster in one direction or in the other direction. Okay. Now, imagine that you have a hill that goes continuously down all the way out to infinity. Okay, we can imagine such a thing. Okay, so we have a gigantic laboratory and it's infinitely big, and this hill is going down, 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 down forever and ever in a gravitational field. So the gravity is pulling things down. Now, imagine you give the ball a push and it begins to roll, and it continues rolling faster and faster and faster. And let's forget about relativity and the speed of light and so on. We'll just take elementary classical mechanics. This ball continues rolling faster and faster and faster, and you know perfectly well what's going to happen. It's going to go off to infinity, going faster all the time. And the question is, how long does it take to get to infinity? That's an interesting question. Okay. Now, if this hillside, the simplest kind of hillside would be a parabola. Okay. You know what a parabola is. If you throw a ball in a gravitational field, and you ignore air friction, the ball will travel in a parabola. A baseball that's hit flies in a parabola and it comes back down. Okay, and the equation for this hill, if you want to plot it, would be minus x squared. Okay, or minus a constant times x squared. Okay. If you have a parabolic hill, how long does it take for the particle to get to infinity? And the answer is, it takes infinitely long. Even though it's speeding up all the time and going faster and faster and faster, it does not get to infinity until an infinite amount of time has passed. So it is always moving away toward infinity, but it isn't there yet. So this is kind of a Zeno's paradox, right? Zeno says, I try to walk to the door to leave the room, and I walk halfway to the door, and then I walk another half of the remaining distance, and half of the remaining distance, and half of the remaining distance, and so on. So I never get to the door. Okay, that's not a paradox. Zeno was wrong. You do get to the door, and the reason is that you walk half of the distance, and then you walk half of the remaining distance, but it takes half as much time. And you walk half of the remaining distance, but it takes half again as much time. And the sum of 1/2 plus 1/4 plus 1/8 plus 1/16 is 1. So how long does it take to walk to the door? 1 unit of time. And then you're out the door. So he was wrong. However, this is a good example this is the modern version, if you like, of Zeno's paradox, because you're always traveling out to infinity, going faster and faster, but you don't get there. Okay, now here's the interesting part. If the hill is not as steep, so it's not minus x squared, let's say it's minus x to the 3/2 power. Okay, so it doesn't go down as steeply. Because it doesn't go down as steeply, if you're rolling off to infinity, it takes, still, of course, it takes an infinite amount of time, because although you're speeding up, you're not speeding up as fast. Okay, so you will never get to infinity. And if the power of x is less than 2, you will never reach infinity. But if the power of x is bigger than 2, so you have a minus x to the 4, okay, minus x to the 6, or minus x to the 2 plus a little bit, 2.1. That's a hill that's steeper than a parabolic hill. Now you will get to infinity in finite time. So you'll be speeding up as you go. So 2 is the critical number. Okay, so if the power of x is 2 or less, you never get to infinity, although you're going faster and faster. But if it's more than 2, 2.1, for example, you will get to infinity in finite time. Okay, so you can imagine a hill like minus x to the 4. So it's a very steep hill. Okay.
Can I ask?
And as the particle rolls down the hill, it gets to infinity in finite time.
So then what happens at t plus 1?
Well, that's the question. And that's a question that you cannot answer using only real analysis. If you refuse to think about the complex plane, you say, I can't see into the complex plane, I refuse to think about it, then the question is, where is that particle? So if it takes time t to reach infinity, where is it at t plus 1? Okay, now, what is the mathematical, first of all, what's the mathematical problem with understanding what happens? And so what happens is this. If you try to understand what's happening as you approach 2 and get past 2, get higher than 2, mathematically, you reach what is called a singularity. So if you study the mathematics of this problem, at when the power, let's consider the function x to the p, or rather minus x to the p, okay, and ask what happens as p passes 2. You reach a singularity, and the only way to understand that singularity would be to go through it, but you can't walk through infinity. The only way to understand infinity would be to go around it. Okay? And if you go around it, you're using the complex plane. Because going around something on the real axis, if you bump into something on the real axis, the only way to get past it is to make a little detour into the complex plane. Okay? If you analyze it using complex variables, now complex mathematics, okay, now you discover something extraordinary. Okay, so there are 2 possibilities. Either the particle rolls off to infinity, it reaches infinity at time t, okay, and at t plus 1, it's still there. That's one possibility, okay? But another possibility is that if we allow for the existence of the complex plane, okay, so let me take a momentary detour. If you only believe in real numbers, you know two infinite numbers. One of them is plus infinity, and one of them is minus infinity. And they're infinitely far apart. Okay, you can walk off to the right, and I guess this is your right. You could walk off to the right, and you will, after an infinite amount of time, reach positive infinity. Or you can walk off to the left, and you will reach negative infinity. And those two infinities are infinitely different. One is plus infinity, the other one is minus infinity. Okay. But in the complex plane, how do you define infinity? Okay, so infinity is defined as the limit of 1 over x as x goes to 0. But there are many ways for x to go to 0. You can approach 0 from the positive direction or the negative direction or the complex direction. Many, many ways. This is a two-dimensional plane, so there are many ways that you can approach 0. And the answer is called infinity. And there is no difference between positive infinity and negative infinity. They are the same point. And so the other possibility is that this particle will roll off to infinity, reach infinity in time t, and then come back from infinity on the other side and return back to the origin.
Could I just stop you? So this function 1 over x. So if I approach x equals 0 from the positive direction, this blows up. If I approach it from the negative direction, it also blows up. But it blows up negatively. It blows up negatively, but they're the same point on my plot, I can imagine it as. And that's the point.
The point is that in the complex plane, there is a unique point at infinity. Okay, and it is called infinity. And plus infinity and minus infinity are the same point. Okay, so if I go to infinity off at some oblique angle or something, just in the complex plane, all of those bullets that I'm firing off in the complex plane reach the same point at infinity, which is 1 over 0. 1 divided by 0 is that unique point. And the answer is, what do you mean by 0? 0 is a number which can be seen as a limit of a complex number as its distance from the origin gets smaller and smaller. Okay, so there's a unique point. So when this particle runs off to infinity in one direction and it reaches infinity in finite time, it is not only at that infinity out there, but it is also at this infinity here. Okay. And it's moving very fast in that direction, going this way. But now it's at that point, and it's still going that way. It is instantly, it goes from this point to this point, and it is still moving this way. It's not moving that way, it's moving this way. So it didn't change. In order to change direction, someone would have to exert an extreme force on it. So it's moving this way. Okay? Which means it's starting out at infinity here, moving this way. So what does it do? And moving infinitely fast. Okay, what does it do? It rolls right back up the hill and comes back to where it started. Okay? And this is not just talk. This is a rigorous result mathematically.
But so then it spends most of its time on the real axis, and only a very small amount.
No time off the real axis. Why? Because when it goes off in this direction, you can think of it as whizzing infinitely fast until it gets to the other infinity on the real axis and rolls right back up the real axis. So if you ask, where are you likely to find this particle? Okay, you're likely to find it where it's moving slowly.
Mm-hmm.
Okay.
So then the idea would be,
for example, my mathematical advice to you, if you would like to cross a street and you don't want to get hit by a truck, you would like your probability of being on the street where the cars are and the trucks are, you would like to be moving very fast. So the best way to cross a street, especially if you don't want to look and see what's coming, the best way to cross the street is to run at extreme velocities, because you won't get hit, because the chance of you ever being on that street is very small. So the chance of being hit by a car or a truck is very small. Okay. So the same is valid here. You're going very slowly when you're at the top of the hill, but you move faster and faster and faster as you roll down the hill. So you're very unlikely to be far away. Very unlikely to be very far away. And you're very likely to be at the top of the hill. So in this situation, in this scenario, where are you most likely to be? So again, I put you at the top of the hill and I give you a push, a little push in some direction. Where, after that point, where are you most likely to be found? And the answer is at the top of the hill. Okay, because that's where you are moving slowest. Everywhere else, you're moving faster. You go faster and faster and faster off to infinity. You come back from infinity moving very, very fast. You slow down as you reach the top of the hill. So you're most likely to be found at the top of the hill, or in a very small region about the top of the hill. So this is called dynamical stability. So you're statically unstable. Okay, if you're balanced at the top of the hill, it's very precarious. So you're statically unstable. But if you're moving, you are dynamically stable. You've seen circuses, you've seen a clown in a circus balancing a broom upside down. Mm-hmm. And you notice that the clown doesn't take this broom and hold his hand still. The clown is moving his hand, and if the clown did not move his hand, the broom would fall over. And that's because the broom is statically unstable. But what the clown does is he moves his hand, and if you move your hand, the broom doesn't know which way to fall. So it's balanced. Okay, and that's dynamic stability. And the same is true when you ride a bicycle. That is a bicycle that's not moving will fall over, but a bicycle that's moving will not fall over.
So I understand the picture. Are you implying that? So in the real world, when we measure something, it's always that person weighs a real number of kilograms, and that person over there is traveling at some velocity that's some real number, of course with some units. Is the picture you're painting that in the real world, when we take measurements, we see real numbers because we have some dynamically stable scenario where the particles we measure are most likely to be around, this zero on the real line? because the scenario you drew is in some sense contrived, right? This potential of minus x to the 4. So I want to understand. Is this the image you're trying to paint, or do you have some other purpose behind the sort of analogy?
Well, the reason for making for going through this argument is that here we're talking about physics, not mathematics, but physics. And what we're saying is that the physical situation of a particle balanced on top of a hill is not a unique situation, that there are two possible outcomes. Instead of a ball, if you imagine me pouring water on top of the hill, okay, you could imagine the water flowing down the hill and disappearing away. And that's not what we're talking about. We're talking about a different situation where I give the water a push and it flows down in one direction and it comes back up in the other direction. Okay. So it's making a circuit. Okay. It's continuing to flow. And this is an example of a problem with a balanced loss and gain. Okay, and that's this is the physics that I've been studying. And
could I pause you there then, just because I do want to get into that physics, but I think so. The what you're referring to is your work in PT symmetry,
right?
And I want to get into that, and I want to get into analytic continuation and eigenvalue problems first, though. So just sorry to stop you, but so that we don't lose some people who aren't familiar with some of the basics, could we take a step back, and would you be able to give, because this is the framework in which these sort of ideas are described, could you give sort of at a conceptual level an introduction to what quantum mechanics is and what the Schrödinger equation is? Because I want to step into your work on eigenvalue problems and analytic continuation there.
Sure. Let me just say, before we do that, though, you might say, this is ridiculous because I would like to study motion on the real axis. That's what I would like to study. But I'm sorry, but you can't, because that is not reality. Okay. So what I gave you is a constructed version of complex motion. Okay. Using classical ideas. And we could have a big debate about whether or not there are whether the world is real and there are two infinities, or the world is complex and there's one infinity. And we could have some sort of philosophical discussion. And I would argue that the answer is specifying a physical problem with a hill is not a unique specification. There's more to it. Okay. And there are two possible outcomes. Okay. And both of them are equally allowed. Okay. They're equally allowed in the sense that if I have a radioactive particle, it can decay out to infinity. And that's one possible outcome. Another possible outcome is that you could have a balanced loss and gain, where stuff is coming in and stuff is going out. And the particle, although it's unstable, doesn't decay in that sense. And we can discuss the problem, but basically my argument is you haven't uniquely specified the problem until you tell me the setting, whether we're talking about a complex setting or a real setting. Okay, so that's the first comment. The second comment is that the world really is complex, and it isn't just real. And that's because we now know of phenomena which are quantum mechanical, which are undeniably complex. Okay, and such a phenomenon, and this is in some sense what distinguishes what distinguishes classical mechanics from quantum mechanics. And quantum mechanics involves complex motion, and you cannot get away from it. Okay, it really is complex. And the simplest demonstration that it is complex is to have a hill, as before, okay, and we fire electrons at this hill. Okay, this is a potential hill. Now, if these electrons were classical billiard balls or baseballs or something, they would roll up the hill, eventually come to a stop, roll back down again, and go away. Okay, and we could agree to that in a finite laboratory, where we're not talking about the ambiguity of infinity, which is what this problem is about, but we're in a finite laboratory, the particle would roll up the hill, and its motion would be unique. It would come back down again and go back. Okay. A quantum particle won't necessarily do that. So if you fire an electron, which is a microscopic particle, and that a particle that obeys the laws of quantum mechanics, most of the time the particle will encounter the hill and bounce back. But some of the time, it will penetrate through the hill. Okay, now in order to go through that hill, it doesn't have as much energy as required to get above the top of the hill. Okay. But nevertheless, even though it doesn't have enough energy to go above the top of the hill, it will go through the hill and come out the other side. Okay. And we can ask, how did the particle do that? How did it go through the hill even though it was energetically forbidden? Okay. And classically forbidden. And the answer is, well, people invent words to describe things they don't understand. Okay. So what people do is they say the particle tunneled. Okay. What does that mean? Well, it means that it left the real world, entered the complex world, and if you want to think of the trajectory of the particle as a path, you have this vision of the electron always existing. It cannot disappear. You've never seen something disappear and come back again. So it must exist, but it doesn't exist in the real world anymore when it's tunneling. Where is it? And the answer is, it's in the complex plane. If you insist on following the trajectory of the electron, it goes into the complex plane, okay? Now, things are complicated because quantum mechanics says that particles are wave-like and so on, and I won't go into that. But basically, if you want to follow the trajectory of an electron when it's tunneling, the only way that you can understand how it comes out the other side is that it has taken a detour into the complex plane, returned back to the real axis, and continued on. Okay? And so what I'm arguing is that the complex plane is not just a beautiful mathematical construct, but starting in the 1920s, which is very late, people began to realize that the complex plane is necessary to describe some physical processes, namely microscopic physical processes. Macroscopic physical processes don't seem to require the complex plane, although complex mathematics is very useful in understanding equations. Okay, so you understand, so, all of the classical theories like classical mechanics, astronomical motion, orbital motion, and so on, fluid dynamics, electricity, those are 19th century theories, and were developed to a very high level by the 19th century. And even in the 20th century, relativity, special relativity and general relativity, gravity, don't seem to require complex numbers. Mm-hmm. In fact, later on, it was discovered that they do, but before the 1920s, nobody had any idea that you were required to use the number I. Okay. Mm-hmm. But even in special relativity, you do need to use the number I. Okay. And I can talk about that later. Okay. But what I'm saying is that you can't avoid it. The complex number system is actually, I was going to say really, but I shouldn't do that. That's a pun. Okay. It's actually present and determines not just the behavior of mathematics, real mathematics, but it determines the behavior of real physics that we are measuring. And that is what quantum mechanics does.
So one scenario that immediately pops into my mind is electrons bound in an atom, right? When you first learn about quantum mechanics, we learned that electrons can't take any sort of energy within inside the atom, but they exist in sort of quantized states, and right. that they transition between these states. Mm-hmm. Do you have a picture for what happens as they're transitioning between the states? Is that similar, where there's sort of a complex space in which they travel through?
Yeah. So, long time ago, when I wrote my thesis, I began to realize that this picture that we have of what you're describing is the quantum mechanics that was being developed in the 1920s and later in the 1930s. And we say that a particle in a potential, so this time it's a right side up potential, okay? So, if you had a classical particle in a right side up potential, it would be a particle that's rolling back and forth in a potential hill, okay? And classically, you would say you can give this particle any amount of energy that you like, but quantum mechanically, we learn that only discrete energy levels are allowed.
Okay. Could I stop you just for 1 second? So there will be lots of people who don't understand the connection between the potential and the atom scenario, where you have an electron that's bound. Could you just say a few words there just to clarify for some people?
Right. So a potential is described using units of energy. Okay. So in general, a particle has a certain amount of energy. It has kinetic energy, which is energy of motion. If it's moving faster, it has more energy, okay? And it also has potential energy. So if it is subject to forces, such as the force of gravity, a particle, if you raise it up, has more potential because it's higher up in the gravitational field. So it's not moving, but it has more energy, okay? And if a particle is moving in a gravitational field, some of the energy of the particle is the energy of the motion, called kinetic energy, and some of the energy is potential energy, which means how high the particle is. If the particle goes lower, it will be going faster. And if it's higher, it will be going slower. If you throw a ball up into the air, at first it's going fast. It then goes higher and higher and higher, and some of its energy of motion, becomes potential energy. And that potential energy is being stored in that particle. Eventually it may stop and then start falling down again. And as it falls, it loses potential energy, but it gains kinetic energy, okay? In an atom, you don't have gravity, but you have electrical forces, that are holding the electrons in the vicinity of the nucleus. Okay, if you think of this as a classical system, you might think of it as a solar system, where the planets that are far from all the planets are held together by the force of the sun, the gravitational force. The planets close to the sun are moving very quickly. The planets far from the sun are moving slowly, but they have a lot more potential energy. Okay. So if you think of an atom that way, which means classically, you would say, I can put a planet in any orbit I like. It could be at a radius of 1 mile, 2 miles, 3 miles, 7.9 miles. It doesn't matter. Okay. But quantum mechanically, that's not what happens. It's very interesting that planets, which are acting classically, can be any distance from the sun, and they can have any amount of energy you want them to have. But in an atom, an electron can only have a given amount of energy, and that can be demonstrated in the laboratory. Okay, so the naive picture, if you want to think of the electrons as being as moving in a real sense, that is, moving about back and forth inside the atom, you have some sort of fog of electrons that are moving around. You don't know where any of the electrons are, but a given electron is not allowed to have any amount of energy at once. I can't do that. It has discrete energy levels, and these are called energy levels or states. And the electron can be in a state of this much energy, this much energy, this much energy, and so on. Okay, those are energy levels. And you can see those energy levels when you allow the atom to interact with light. And you can see, when you look at you do a spectral analysis, you can see the specific energy levels. Okay, they're very visible. Okay, now, and furthermore, you can predict them mathematically. But what is very interesting is that the picture is more complicated than that. You can, instead of studying the atom on the real axis, you can study the atom in the complex plane. And in the complex plane, the possible energies for the electron are continuous. They're not discrete. Okay, that's an amazing result. This is the work that I did in my thesis, in fact, a long time ago. And so why is it that they look discrete? And that's because we live on the real axis. And so when we see an electron, it can only have this much energy, and so on. But in the complex plane, the electron can have any energy as it moves off into the complex plane. But when it crosses the real axis, it can only have these discrete energies. So what was continuous is actually, what is discrete is actually at a higher level, at the complex level, is actually now continuous. The way I describe this, if I'm giving a lecture on this, is I say, imagine a parking garage. Okay, you enter the parking garage and you see that the parking garage has distinct levels. It may be a 5-level parking garage. You drive into it, but in fact, you can continuously drive from one level to the next, to the next, to the next, okay? But if you were to take a gigantic saw and cut right through the parking garage and pull it apart, what you would see is discrete levels. But the complex plane says that there's something much more sophisticated going on, and that the levels in this parking garage are continuous. Okay, and you can go continuously from one level to the next, just by moving through the complex plane.
And does the dynamics in the complex plane also work? The calculations you can do?
Absolutely. Absolutely. You can look at the motion as these particles are traveling in the complex plane. And if you want to understand motion on the real axis, you look at the limit as you approach the real axis. And the complex motion is very complicated, but as you approach the real axis, it becomes recognizable as what we know and love. You know, what happens when you throw a baseball. Okay, but in the complex plane, you have more interesting motion.
So famously, quantum mechanics has a number of different interpretations. There's sort of the Copenhagen interpretation and pilot wave interpretations, many worlds and so on. Does this sort of idea shed any light on which of these interpretations may be correct, or are you able to say something deeper because of this insight, this analytic continuation?
So it's when I was a graduate student and I was getting ready to begin my thesis work, you have to take a qualifying exam to demonstrate that you are qualified. You've successfully passed all of your required courses to go on to a PhD, to write a PhD thesis, that you've sufficiently mastered what you learned in your courses. This is a qualifying exam, and it can be a very difficult exam. It may be an all-day exam, maybe an oral exam, maybe a written exam, and so on. In my case, it was an oral exam, very frightening. Okay, it's the first time I ever stood up in front of a committee of people who were throwing questions at me, very hard questions. My friends who had already passed the exam, of course, gave me some advice. And the advice was, if you don't know the answer to a question, don't try to fake it. Say you don't know. Because if you try to fake it, they will ask you harder and harder and harder questions until they show that you don't know what you're talking about. But if you honestly say, I don't know, let me think about it, you don't back yourself into a corner. Okay, and indeed, when I had my exam, I was asked a very hard question, and I said, I don't know. And one of the people on my committee said, the answer must be this. And another person on the committee said, no, you're wrong. And my whole committee started arguing with each other because nobody was certain about what the answer was to the question. And I felt great because they were ignoring me. Well, you've asked me a very hard question, okay, about quantum mechanics is not, it depends on how you approach quantum mechanics. If your approach is that of a mathematician and you like to solve the Schrödinger equation, for example, as a mathematical problem, that I can do. But if you want to go into deep philosophical interpretation, and there are many different interpretations about quantum mechanics, many worlds and so on, I would say my intuition is that in order to understand quantum mechanics, you have to understand that we live in a complex world, but are only able to perceive real things. And that particles can visit the complex world and come back out into the real world and so on. but I don't know. I can't give you a serious answer about how to approach this problem. Okay, I don't know enough, and I mean, it's a really, really hard question, and I wouldn't even begin to fake it. Okay, I mean, I can tell you about solutions to equations, but when it comes to a very high level philosophical interpretation about what quantum mechanics is very strange, and there are these different interpretations of quantum mechanics. What should I say? My choice is not to say anything at this point. That's a long answer. I'm not. I'm not trying to evade the question, although that's exactly what I'm trying to do. Okay.
I also don't know the
answer.
question. I also don't know the answer. So I'm like one of the people in one of the examiners. But
yeah,
this
is a very, very hard question, and you can see people arguing about, what is quantum mechanics. Okay, I mean, quantum mechanics goes beyond our perception of the world. Okay, because it's what happens in to very, very small masses, and what happens over distance scales that are very, very small. And there are now people are doing macroscopic quantum mechanical experiments, but quantum behavior is described in the small. Okay, and it's different from our perception of the real world. What is also happening is that there are now strange things that are happening in the large. Okay, that is, gravity may be repulsive at gigantic distances, which is very interesting. Okay, and so
is this PT symmetric conformal gravity type directions, or
I can talk about that. I mean, it would be more of a more discussion, but I'm happy to chat about it.
I think that would be a mistake for the scope of this interview, because I think it would take too many steps to get there. But what we can do is we can talk about your research more generally in PT symmetry, because I think that is something that's very interesting that people will be able to follow in a confined bit of time. So let's do that then. If you're happy with that, let's jump into with just the basic question: what is PT symmetry, and what does it mean conceptually?
Yeah. So P, the letter P stands for parity, which means reflecting space. Okay. So it's what you see when you look in a mirror. When you look in a mirror, your left hand becomes your right hand, and so on. So it is a spatially reversed picture that you see. Okay. So that's parity. Okay. And it refers to space reflection through a mirror. Okay. T means time reversal, and we can't physically reverse time, but mathematically we can imagine time flowing backward. Okay, and in fact, Wigner showed that time reversal corresponds to changing the sign of I in the complex numbers. Okay, so there's this deep connection between time reversal and complex number theory. Okay, and so PT symmetric quantum mechanics, what is that? Before I say anything about quantum mechanics, let me still remind you about classical mechanics. Okay, so Einstein's gigantic breakthrough at the beginning of the 20th century was the discovery of special relativity. Okay, it's a fantastic um, discovery. And what he basically said was that if you do a Lorentz transformation, which means that you go from one um, dynamical system, okay, to another dynamical system moving relative to you. That's why it's called relativity. It's moving. So you're moving through space like this. Another system is moving at a greater speed through space. Okay, they can look at each other. And the question is, what about the relative physics between, what is when one person in one space looks at a person in the other, one platform looks at a person on the other platform, what do they see? And they see time dilation and space contraction and so on. They see things that are relativistic. Okay. At a slightly higher level, you describe how one person looks at another person, or how one person is related to another person in terms of a mathematical object called a group. Okay, and they talk about the Lorentz group. So when you perform a Lorentz transformation, you go from one object floating through space to another object floating through space. Okay, so you transform from here to here. Okay, is that clear?
Mm-hmm.
So Einstein gave us something that we didn't have before. He pointed out that, and this is not quantum mechanics, this is classical mechanics, that classical mechanics, in fact, doesn't behave the way you think it's behaving, because all of your world experiences are connected with slowly moving things. When I say slowly moving, I mean much slower than the speed of light. And Einstein shows us that the speed of light is the fastest you can go. And as you go faster and faster and faster, new effects come into play, which you could never have imagined. Okay, namely time dilation, Lorentz contraction, and so on. So the Lorentz group is all possible ways of performing a Lorentz transformation, transforming from one frame of reference to another frame of reference. Is that clear?
Mm-hmm. I can show on screen as well some aids.
Okay, good. So what's an example of a Lorentz transformation? So the simplest possible transformation is you don't do anything. Mm-hmm. You just stay in your same frame of reference. So that's unity. You don't do anything. Another Lorentz transformation is to jump onto a platform that's moving 5 miles an hour faster than you are. Okay? But another very interesting kind of Lorentz transformation would be to reflect space. Okay, that's a transformation. So what is happening is now a mirror image. Mm-hmm. So you're moving this way and you jump onto something moving at the same speed but going that way. That would be a possible transformation. An even fancier transformation would be to reflect time. Okay? So after the discovery of the Lorentz group, which is the set of all possible transformations, infinite numbers of possible transformations, it was believed that if you had a laboratory that was going forward in time and another laboratory that was going backward in time, and they each did an experiment, they would always get the same result. For example, if they measured how long it took for a radioactive particle to decay, or they did a chemical experiment or so on, it would be the same. Mm-hmm. And it was also believed that if you reflected a laboratory through a mirror, you looked at a mirror image, okay, and you did an experiment in this reflected world, things would be the same. Now, in fact, we don't experience this because there are, proteins are in the shape of a helix, as you know.
Mm-hmm.
DNA is in a helix, and there is a left-handed helix and a right-handed helix going in opposite directions, and we only deal with proteins that spiral one way, not the other
Mm-hmm.
way. Okay. However, in principle, you could have left-handed life and right-handed life, but we don't see that.
Mm-hmm.
And it was believed that a reflection in space and a reflection in time are to be included in the set of all possible transformations.
Mm-hmm.
Okay. And it was believed for many years. So Einstein is at the beginning, 1905, right? But much later, 50 years later, more than 50 years later, it was realized that space reflection is not, in fact, an allowed Lorentz transformation. Because if you do a space reflection, you get different physics.
Mm.
And that's unbelievable. I mean, it's amazing. I would never have believed it. And that, of course, was, Li and Yang, and they won the Nobel Prize for it. And
so could I stop and sort of reiterate what you've said, just to make sure I understand exactly and that others are following?
Mm-hmm.
So you have this symmetry group. You can change your frame of reference. You can do rotations of your reference frame, for instance.
Right.
But you're talking about discrete transformations like reflection symmetry. So you turn a right-handed frame into a left-handed frame.
Right.
And it was believed that those were also symmetries of nature, just like...
Because they are elements of the Lorentz group as it was mathematically formulated. Okay.
But then you do an experiment. It's not.
To put it differently, there is a light cone, which basically says that the speed of light is a unique speed. A particle if it were moving at the speed of light, would satisfy an equation called the light cone condition.
Mm-hmm.
And that says that x squared plus y squared plus z squared minus t squared is a constant. Mm-hmm. Okay. And a space reflection means x goes to minus x, y goes to minus y, and z goes to minus z, but they're squared.
Mm-hmm.
So the minus sign doesn't make any difference. So it's obvious that parity should be a symmetry. Why should it be that if you look in the mirror, there's a different world? And nobody imagined that possibility. But it is different.
Mm-hmm.
They are not the same world.
So this is the weak force, right? Which is chiral?
Right. Very, very good. So strong forces.
Do you mind if I pause? So sorry, because I think this is a topic that will confuse people. So what you're saying very basically at its core is physics shouldn't depend on the way that you look at it, right? It should be invariant under Bob or Sue looking at it from different directions, and so you can change the frame at which you're looking at the physics, and so that includes rotations, these sort of things, as I said before. And we assumed a different way of looking at things that wouldn't change the physics was just doing one of these inversions, sort of in space, this sort of changing from a left frame to a right-handed frame. But in experiment, that's not true. We find surprisingly, amazingly, that this is not just a different way of looking at nature, but that it really is different physics if you change the frame.
Righto. Now, there's a second discovery that happened after Li and Yang, which was verified by experiments that Madame Wu did a year later to So they did the theory, and Madame Wu did the experiment. It was realized by Cronin and Fitch, who also won the Nobel Prize, that time reversal changes the physics. That is, a laboratory going backward in time will get different experimental results than a laboratory going forward in time. Okay. So the group of Lorentz transformations is much smaller because it cannot include the element P or the element T. Okay.
Could I ask you just sorry, this is something that people are going to wonder about. How on earth do you set up an experiment that's going back in time?
Oh, of course you can't, but you can. You need to. Of course, you can't have such a laboratory, but you can interpret a particle spinning one way as a particle that spins the other way, but is going backward in time. That sort of thing. Okay, so you can spin it up this way, and you could spin it up that way, and so it's the motions of the particle that are reversed. But of course, you can't go backward in time. You can't directly do that. So yes, the experiment is inferential in that sense. Okay, but it is a clear experiment. Okay, so physics that is time reversed is different physics. Okay, and this raises a very, very interesting question. What happens if you reverse space and time? Okay, so the point about the Lorentz group is that we're talking about space-time. And if you want to be mathematical about it, we don't want to distinguish between space and time. It's simply four-dimensional space. Okay? And if you reflect part of it, that's no good. And if you reflect the other part of it, if you reflect the three space dimensions, no good. The one time dimension, no good. But what if you reflect all four? That seems to be much more symmetric in a way, because we're talking about four-dimensional space. Change the sign of all four dimensions. Okay. Now, there is a theorem, a very famous theorem, called the CPT theorem. And what it says is that if you reflect space and you reflect time and you change particles into antiparticles, then you will get the same result. Okay, now not everybody believes the CPT theorem, and people do experiments to see if they can find violations of that theorem, but they haven't been found. So there's something very special about the product of P and T. Not P separately or T separately, but PT. Okay? And what we were talking about very early about the classical physics and infinity and complex motion and so on, those are PT. We did PT reflections. I didn't call it that, but those are PT reflections. So let's put it this way. What would PT symmetry, what is PT symmetry? Okay, so imagine that I have a pail and I'm pouring water into this pail. Well, the pail will be filling up with water, so the pail is not in equilibrium. There's more and more water all the time. Okay, and suppose I have another pail over here, and there's a hole in this pail, and the water in the pail is draining out. That pail is not in equilibrium because it has less and less water. This situation, however, is PT symmetric. Okay, in the following sense. If I reflect space, then the pails are interchanged. But if I reflect time, the water going out becomes the water going in, and the water going in becomes the water going out. It reverses direction. Now it's the same.
So if I switch the buckets and reverse time, the image remains the same.
Right. So that's an example of a PT symmetric reflection. And it's the same.
Mm-hmm.
Okay. Now we can do something else. We can connect the two pails with a pipe. And now this system is a very strange system because water is flowing into one pail. It's now flowing through the pipe into the other pail where it's flowing out. Okay. This system is in dynamical equilibrium. So the water level in each pail stays exactly the same. It's not changing. Why? Because water is flowing in, it flows to the other pail, it flows out, and the level of water in each pail is the same.
Mm-hmm.
That is what we talked about at the beginning of our discussion. Because you remember I said, imagine that you have a pile of water on top of a hill and it's flowing out. So that's loss. The water is going out, but the water flows around, it comes around and comes back from the other infinity, and it flows up to the top of the hill. So the total amount of water at the top of the hill is not changing. It's a system in dynamic equilibrium. And these two pails are also in dynamic equilibrium. Normally, physicists would say that there are two types of physical systems. There are systems that are isolated. So an atom sitting all by itself, not interacting with a beam of light or X-rays, or it's completely isolated from the rest of the world. This system has a given set of energy levels. Okay, and all those energies are real. Okay, but there's another kind of system which is interacting with the outside world. Stuff is going into the system and stuff is going out of the system. Okay, and that is a system in contact with its environment. Okay, and this system may not be in equilibrium because you may be putting more stuff in than you're taking out, and the system is filling up with stuff, with it, whatever the stuff is. Could be energy, could be number of particles, could be the amount of water, it doesn't matter. Okay, but PT symmetric systems are systems which are similar to both. Okay, in the sense that they are in contact with the environment. Stuff is going in and stuff is going out in a balanced PT symmetric fashion. Okay, but at the same time, they're in dynamic equilibrium. Okay, so these are special new kinds of systems, and they behave very much like systems of one type, isolated systems, and systems of another type, which are not isolated. They're in contact with the environment. So in what ways are the same? Are they the same? Well, they have real energies, or they may have real energies, to be more precise.
Can I ask,
okay.
So the picture that you paint is sort of, it's very intuitive. And because I can imagine a system which is in this sort of dynamical equilibrium, I can imagine closed systems which have no energy or other things coming in and out. And then I can imagine open systems or systems that are in contact with the external world, where there's a flow of energy or temperature or heat, rather, right. or particles. It doesn't seem so crazy to consider these three options, but yet when you first started playing, it was around the year 2000, right? When you started playing around with PT symmetry and quantum mechanics. Why?
Yeah, it was just around 2000, and it was
shocking, right?
I was completely shocked and appalled. I was completely thrown by this.
This is a picture that I want to somehow paint for people. Why was this shocking? Why? Because of course you've given us this nice intuitive picture. Can you sort of reel us back and explain why that somehow wasn't expected, that you would find these three sorts of systems in quantum mechanics?
Right. So this isn't easy, but let me try. When you take an elementary course in quantum mechanics, your very first encounter with quantum mechanics, what you learn is that the very first thing that you study, or among the first things that you study, is a simple atom, like a hydrogen atom. And you learn that the energy levels of a hydrogen atom are all real, and all real energies. There is a ground state, and there are various excited states, and these energies are real. Of course, that's an isolated hydrogen atom. If you connect the hydrogen atom to its environment, the energies are not real. Why is that? Because if you have a hydrogen atom in an excited state, what can that atom do? The atom can drop to a lower energy state and radiate a photon, which carries away some of that energy. Okay, energy is conserved, but a photon, a tiny burst of light, will come out. When we look at a neon light at night, and street signs, lights, especially a neon light or an argon light, what you're seeing is electrons in excited neon atoms dropping to lower energy levels and giving off light, characteristic color of neon light. Okay. So since those systems are not stable, we interpret that as meaning that the energies are actually complex. So in any case, you take your elementary course in quantum mechanics, and the very first question that arises is, when are the energy levels real? And when are the energy levels complex? And there's a condition, a very famous condition, called hermeticity. Okay, and you say that a Hermitian system has real energy levels. And you learn this at the very beginning. And the reason that PT symmetric systems are shocking is that they can be systems that are not Hermitian, but still have real energy levels. Okay, in the sense that in that funny classical model I had of a ball rolling up the hill and going on and then coming back from infinity, it continues on. It's not changing. It's in a fixed state. It's in a fixed energy level state, and yet it's connected to its environment because stuff is going out to infinity and coming in from infinity. Okay, so it should definitely not have a real energy level. What should happen, you would think, is that all the stuff, runs off to infinity and it's gone. It runs downhill and there's no more energy. All the energy has radiated out to infinity and it's gone. And that's sort of our I would say, intuitive picture. If you have something hot, what does it do? It radiates energy. The energy flows away off to infinity and it's gone. So the state was not in a stable state. And yet what I've argued is that if you include the complex plane, now you can have states that are connected to their environment. Particles can flow out to infinity and come in from infinity, and the state is stable. Okay, it's in dynamic equilibrium. Okay, so it can radiate, it can be connected to its environment, and yet not change. And mathematically, I mean, I'm not going to give you the mathematical condition, but this is a state that violates this elementary condition of hermeticity and yet has real energies. Okay. So as I say, when I first took my quantum mechanics course, in the first week or two, the professor said, the way you know if there are real energies corresponding to states that are stable, unchanging in time, in equilibrium. If the energy is real, the states will not be changing their physical properties. And that's this character, this is the condition of hermeticity. And here I am talking about physical systems that are not Hermitian, and yet they're not changing in time. So this is a whole new class of quantum mechanical and classical mechanical systems, like the pails of water, that's just classical physics, which are connected to their environments, and yet they're stable. And this requires the use of complex variables. Okay, the mathematical underpinning is based on complex numbers, but we know that complex numbers are really there in physics. They're required. I mean, at the very beginning of quantum mechanics, you have complex numbers. Okay.
It's funny. I should point out that when I went through my physics undergrad, this condition, this hermeticity condition, is still hammered into you, right? This is the quantum mechanics greats Heisenberg, and from there onwards, I suppose, this has been hammered into person after person after person. And so it's so heavily ingrained that it really is shocking. Can I just ask, so that there are physical systems, right? You can go away and you can do an experiment. This has quite wide applicability.
Let me say it, just to make sure, let me say it right. I'm not saying there's anything wrong about hermeticity. The statement is, if you have a physical system that is described as a Hermitian one, that is the equations for the system are Hermitian, then the energies will be real. I'm not saying there's anything wrong about that. Okay. What I am saying is that if the system is not Hermitian, which means that you are working in the complex plane, the energies can still be real, and the system can still live in a stable state. That's the surprise. Okay, so what it means is that there are huge numbers of new physical systems that we can study. Okay. So I mean, if you want a serious example that you can, that has been performed in a laboratory to verify the equations that we have written down, here it is. Here's an example. Okay. Imagine you have a fiber, a very thin fiber, and light is flowing through the fiber. This was the earliest example, an incredibly beautiful example of a non-Hermitian PT symmetric system. So light is just traveling down this fiber. Okay. Now we have a second fiber. Okay. And light is also traveling down the fiber. Okay. So you put light in one end of the fiber and it comes out the other end. Is that clear? And so we have two fibers. Now, it's a physical fact that if you put two fibers close to each other, light can leak out of one fiber into the other fiber. So, for example, if you have a fiber with no light in it and a fiber with light flowing down the fiber, and the two fibers like this, say the two fibers are in contact, then light traveling down the blue fiber here will wind up in the black fiber. So no light is going in at this end. in the black fiber. Light is going into the blue fiber at this end. But because they're near each other, most of the light is coming out of the blue fiber, but some light has leaked into the black fiber and is coming out. Okay? That's just straightforward optics. What I can do is consider an equilibrium situation. Remember, we had an equilibrium situation with gain and loss. Okay, so imagine we have these two fibers. Okay, let us remove light. Let's remove light from the black fiber. So how do you remove light? How do you absorb it? Well, one way is to plate the fiber, to cover the fiber with metal. So you just put a little chromium on the fiber and the light energy will be sucked into the chromium and the light will disappear. Okay. How do you put light into a fiber? Well, you shine a laser on it and that introduces light into the fiber as it's flowing. So not at the where the fiber begins or where it ends, but you just shine a laser light, say midway down the fiber, and that will induce light to flow down the fiber. So these are the two pails of water with loss and gain. Okay, and a pipe between them is simply that the fibers are touching each other. Okay, and there's light leaking from this fiber into this. So this system is PT symmetric because light flowing in and light flowing out, if we reverse time, looks like this. But if we reverse space, it looks like this. So you recover the original situation. Okay? So that's an example. That was the very first experiment verifying the mathematics behind a PT symmetric system. And since then, there have been countless numbers of experiments, many, many, many experiments, mechanical experiments, electrical experiments, and these systems have remarkable properties. They're new, they're very interesting. I mean, now there are something like, there are approaching 10,000 papers have been written on systems with PT symmetry. Okay, the citation, I mean, we're talking about published papers. By the end of this year, it will exceed 10,000 papers at the rate that it's going. So lots of people are working on this. This is a very busy, active field.
Can I ask, what makes a good question physics to study, to work on?
Let me tell you about me and my life at my university. So I love solving problems, as you might guess. I love mathematics. I love solving problems. And there is an exam called the Putnam exam, which is taken by college students. The Putnam exam is a 6-hour mathematics contest. Okay, and the top mathematically inclined college students often take this exam. Every year, several thousand students take the exam. Okay, and the exam is 6 hours long, and there are 12 problems on the exam. So in fact, the exam is 3 hours long in the morning, a 2-hour break for lunch, and then 3 more hours. So you have to solve 6 problems in the morning and 6 problems in the afternoon if you want a perfect score. Essentially, nobody gets a perfect score. Okay. Solving one problem means that you're pretty much in the upper quarter of the people taking taking the exam. It's a very, very hard exam. And if you solve 2 problems, you are doing spectacularly well. I mean, it means that you're very, very talented. So it's rare, but the top person in the country, there are big cash prizes and scholarships and so on. But the top person in the country may solve typically 9 problems, maybe even 10. In the past, it has happened that someone has solved all 12, but basically it's virtually hopeless to be able to do that. Okay, so they give you a feeling. Okay, so I love solving problems. And when I began my teaching here at Washington University, I noticed that nobody was coaching kids to prepare for the Putnam exam. And I announced that I was the coach. I just said, I'm going to teach, I'm going to have practice sessions to prepare you to take the Putnam exam. And lots of kids were interested in mathematics, and they attended the practice sessions, and we learned how to solve problems. Okay, which is an important aspect of being a physicist. A theoretical physicist, you have to learn how to solve problems. And this was very effective, because that year, out of the hundreds of schools, there are something like 400 and over 400 schools, 425 schools, something like that, colleges participated in the exam. Washington University came out second. I mean, it helps to learn how to solve problems, hard problems, really, really hard problems. And the year after, in fact, we came in first in the country, top team in the country. Okay, and we were virtually always in the top 10. And it's because the students are bright, but also the students learned how to solve problems in these practice sessions, which is really good. Okay, I mean, and it was wonderful. They did very well. You would think that when they went on to if they became theoretical physicists, you might think that these kids all became professors of physics, but they didn't. And that's because there's another aspect of science which they were not prepared for. And that is that in physics, not all problems can be solved. But on the Putnam exam, every problem can be solved. That is, it may be very hard, but you know before you even see the problem that there is a solution, and that typically is beautiful. Okay? You know you can do it. And that gives you a leg up, because knowing that there is a solution is the first step in being able to solve a problem. I mean, it's what generates it's what brings up your intuition. It gets you into the right frame of mind. The problem with physics is that not all problems can be solved. And if you're going to be a successful physicist, you have to know how to pick a problem. So some of the top kids in the Putnam exam never go on to a career, a scientific or a mathematical career, because they don't have an intuitive feeling of how to pick a problem that you can solve. It's not just solving the problem, it's that you have to find the problem. Okay, so there are 2 ingredients to being a successful physicist or a mathematician. You have to pick a problem that is hard enough to be deep and interesting. You know, you don't say, I'm going to publish a paper on how much 1 and 1 is. That's stupid, right? So you have to pick a problem which is deep and subtle, but still within the realm of possibility of being solved. And finding a problem is a very rare ability, finding an appropriate problem to make, that is, it's a big enough advance in physics to be significant, but a small enough advance that you can solve it. Because I can pose for you a very hard problem in physics, but I have no idea how to solve it. So I wouldn't attempt to solve it. Okay, there are lots of these problems. Okay, I mean, for example, the nucleus of an atom contains protons and neutrons, but they have different masses. How do you calculate the difference in the mass of a proton and a neutron? And why is the mass different? And can you quantitatively calculate that amount of mass difference? They don't weigh the same amount. Okay? That's a very, very hard problem. And at this point in my life, I wouldn't try to solve that problem because I don't know how to begin. And I could waste a lot of time trying to solve something that I'm not equipped to solve. Okay, so I've learned, so the most brilliant problem solvers don't necessarily become effective physicists. Effective physicists, or scientists in general, know how to pick a problem that they can solve, but will still be significant. That's a very hard thing to teach. I don't know how to teach that. It's something that you have to have a tremendous amount of experience, but it's not something you can teach as a rote piece of information in a lecture. This is how you behave as a physicist. Okay.
It's a little bit of a shame that there's no pathway to couple those students that are really good at solving problems with those students that are really good at picking problems.
In fact, that does happen. There are sometimes groups of, this is why physicists are very sociable. They don't work alone, and they talk. This is the reason why physicists talk with theoretical physicists talk with experimentalists. This is why we have seminars and colloquia, so we can learn about problems that are interesting and important. And then if we're a good problem solver, we might focus on maybe not the whole problem, but an aspect of the problem. For example, although I don't know how to solve the question I just asked about a proton and a neutron, I can make a model. Okay, so instead of taking a proton and a neutron in our four-dimensional space, what about a proton and a neutron in one-dimensional space? That's a much simpler question, and I can solve that problem. Okay, so I can simplify the problem by making a model and learn about aspects of the problem without doing a complete solution. If you solve that problem, you're going to win a Nobel Prize, right? In general, if you solve a really, really hard problem. That's very rare, but you still have to earn money, So you pick a problem that's not so hard, but is still interesting.
There's a famous saying from Feynman. He said a lot of things, but one of the things he said, every physicist has heard this "shut up and calculate" mantra, right? Can you say what are your thoughts then on that way of thinking?
Well, let me tell you about Feynman. So to begin with, Fleischman, so my uncle was a high school teacher, a high school physics teacher, in fact. And he was Feynman's high school physics teacher. Feynman in high school was very, very smart. And my uncle just put him in the back room and said, here's a book, read this. But you don't need to sit in my class. Okay. So I had a lot of interaction with Feynman, and also his sister, who's very smart. And so I and two colleagues worked on some papers over the summer at Caltech, where Feynman was, and we used to eat lunch with Feynman. He happened to be around that summer, and we ate lunch, and he would always say, so how's it going? In fact, he didn't say that. He would say, how's it going? Okay. And the three of us would say, well, we showed this and this, and we were able to calculate this, and we established this. And he would say, very good, very good. And then he would say, BS, except he would say that word right away. And he would say, nope, you're wrong, because of this and this and this, and this is inconsistent and it's not correct. And we would be stunned, because Feynman was very, very smart and very, very fast. In fact, he's the fastest guy I've ever known. And the three of us didn't have an answer. I mean, he had picked apart our calculation because he looked at it not in a technical way, but he looked at it from above, and he brought to bear some basic physical theorems and questioned our assumptions and so on, and found what was apparent. He found apparent violations of sensible physical outcome. Okay. And we would go back to the office and work together, the three of us, all afternoon, arguing with each other about what to do and why this happened and what was the violation due to. And much more often than not, we found that there was a flaw, there was an assumption that Feynman had made in his argument that we couldn't catch on the fly, sitting around a cafeteria table. We couldn't do that. But we saw through it, and we would include this, take account this fact. And we got it to work again. And the next day at lunch, Feynman would say, so how's it going? And we would say, well, you assumed that this and this were true, but they aren't, because we made this delicate assumption at the beginning, which forbids this possibility from occurring. And so there is no contradiction. And he would say, very good, very good. Okay. And he was never, by the way, he was wonderful, because it was never a destructive criticism. He didn't benefit by putting us down. He was only interested in physics being done right, okay, and things being done logically and correctly. And if he saw that it was working, he would say, very, very good. But very often it would turn out that he would say, but you're wrong because of this. And once again, we'd have to go back to the office and repeat the process over and over and over. You can imagine by the end of the summer, boy, did we have a fantastic piece of work. We published 4 papers at the end of the summer on our research effort. And that was wonderful. That was an incredible experience, okay? Because physics is a very social endeavor. It's not sitting in your room alone. It's interacting with people and bouncing ideas off each other. And it's because physics is not entirely rigorous. It's based on certain assumptions. The mathematics can be a little bit vague. and making precise statements is very difficult. So physics is interesting because of that, right? It's not like a dry axiomatic mathematical system. So it's very mathematical, and you have to be very careful. So I would say this is sort of care, great care, but not necessarily rigor. Okay. And physics has something that mathematics doesn't. Because after you come up with a finished product, you can test it in the laboratory and see if you're right. Okay. And mathematics is mathematics. It's either rigorously right, that is, it's in agreement with your axioms, or it conflicts with an axiom. So physics is very similar, but it isn't rigorous. Okay. And in physics, you can make approximations so long as they don't destroy, they're not in conflict with your assumptions. Okay. So this is a distinct field. It's an interaction between what you see in the laboratory and what you do on paper. Okay. Mathematics doesn't have a laboratory. You're either right or wrong.
So in some sense, you can run much faster by dropping rigor, because at the end of the day, you can do the experiment.
Yes, you can. I don't know if you say run faster, because there are times when you're really slogging along at a slow pace. But yes, you can. You can. If you drop rigor, it is true that you can get lots of results that appear to be correct, but have to be verified. And some of them will, in the end, not be valid. And that's because your experimental test is violated and your conclusion is not correct. That's just
sort of
not
jumping
correct.
off the cliff and building the bridge underneath yourself as you go, in some
Yeah,
sense.
it may be that one of your axioms is seriously in error. So as far as PT symmetry, it may be that the assumption of PT symmetry, which is more general, is that there may be something flawed about it. Of course, that's not going to happen, because there are already many PT symmetric systems that have been studied and the predictions are correct. But it could be that down the road, we will make wrong assumptions about how the world is supposed to behave, and it doesn't behave that way. So far, things are going very well, however, which is nice.
So let me just ask in brief detail then. We've already discussed the role of rigor in physics. What role does beauty play, or what role should it play in solving a problem?
Beauty, of course, is in the eye of the beholder. Different people see beauty in different. I mean, you may see something as being beautiful when I don't think it's beautiful at all. Beautiful, I think, for me, means that it's a result that it's deep and unexpected and surprising. Okay. And beautiful also means that there is an extremely clever and unexpected argument for producing that result. Okay. Would you like an example of something that's
Please.
Beautiful and unexpected? I could give you.
I think this is actually quite important, because for people for non-mathematicians and people who aren't doing mathematics regularly, I imagine it's quite difficult to understand what physicists and mathematicians mean when they say that a set of equations is beautiful, or that some system is beautiful, or that you have these situations where you're solving something and it just sort of leaps out at you. I'd like to
Right.
somehow give that feeling to listeners.
Right. So I could give you an example of a problem with what I would regard as a beautiful result, a beautiful answer. I could even give you a simple problem. Sorry, not a simple problem, but a simple sounding problem, which I would say is beautiful. Okay. I don't know which. Maybe I should do both because they're very different. But here's an example of a problem from the Putnam exam, which we talked about before. Okay, it's a very, very hard problem. Okay, and it's a yes or no problem. Okay, so you have a plane, okay, and there are an infinite number of points in the plane. And the question is, can you color all of the points in the plane, assign a color to each point in the plane, assign one of three colors to each of the points in the plane? So you could color this point red, and this point green, and this point blue. And so you walk around in this infinite plane and you assign a color to each point in the plane, red or green or blue. Okay? And the question is, I mean, you can do that. You can assign, you know, if you have a point at this location, it's blue. The question is, can this be done in such a way that if 2 points are 1 inch apart, they do not have the same color? So the criterion, do you understand? So the criterion...
There's also like a cartography related question like this, right?
Yes, it's a little bit. It's a cut down version of the 4-color theorem, if you like. But this is, if you can call it the 3-color theorem. So if 2 points are 1 inch apart, they may not have the same color. But they could have different colors, of course. Can you assign a color to every point in the plane such that this is true? This is a very, very hard problem. But the solution is what I would call beautiful, because it's so simple. But you have to see your way through the solution. And I can give it to you if you like.
Sure,
okay?
Please.
Okay, I'll get a piece of paper. Okay. So here are 3 points, and they are all 1 inch apart. So this is 1 and 1 and 1. Okay. Now, this is an equilateral triangle here. They're 1 inch apart, so they must all have different colors. Okay. So if this point, for example, is red, this must be blue or green. So for example, if this point is red, then this point would have to be different from red, so it might be blue, and this might be green. Or these two guys at the bottom could be switched, but they can't be red. Okay? So we already now know the answer to the problem. So the question is why? Okay? So what I'm going to do is draw another equilateral triangle back to back. Okay? So if this point is red, these 2 points must be blue and green. But since these 2 points are blue and green, this point must be red again, right? So now we know that if 2 points are the square root of 2 inches apart.
They're the same color.
Right. So therefore, and it doesn't matter, square root of 2, square root of 3, who cares? But we can clearly see that this distance is bigger than 1.
Mm-hmm.
It's 1 point something. Who cares? It doesn't matter. So we'll just say that this distance is d. There are d inches from here to here, and those 2 points have to be the same color. And the point is that d is bigger than 1, and you can just see that from the picture. So therefore, all I need to do is to take a point in the plane, which is red, and draw a circle about that point of radius d. So there's a circle of radius d, and every single point on this circle is d distance away from this red point over here. And therefore, every single point on this circle, on this entire circle, is red. So therefore, I will simply draw an arc, a chord, I don't mean an arc, a chord in the circle that is 1 inch long. And these 2 points are both red, but there's a 1 inch separation between them. That's not possible. So the assumption is not possible, that you can't do it. And that's the proof. And that proof, in my opinion, is beautiful because it is so elegant. It's so clever. Okay, and that's an example of something that I regard as beautiful. It was the it was the elegance of the argument that I gave to prove it. The simplicity, the argument didn't make use of any other extraneous clever things about mathematics. It was simply cold logic that led to the answer. It was sharply directed toward getting the answer, and I didn't say anything irrelevant.
A high school student could have come up with it if they were bright.
Of course. In this case, what made it beautiful was the technique of proving it. The actual answer is not so interesting. I mean, do you really care whether or not the answer is yes or no? So here the beauty lies in the proof, much more in the proof than in the answer, because, saying, okay, so you can't do it, so who cares? I mean, that I wouldn't say that's beautiful, but the proof is beautiful. But let me give you an example where the answer is beautiful. Okay, where the proof is more elaborate, but the answer is astonishing and surprising and incredible. Okay, so here's a favorite problem of mine. It's a game. It's just a very simple game with incredibly simple rules. Okay, and the rules of the game are this: you have an opponent who and you're not actually fighting your opponent. The opponent is just your double who's setting up a problem for you. That's all. So what this guy does is he takes a bunch of little pieces of paper, and on each piece of paper he writes a different number down, real number. Okay? For simplicity, we can assume all the numbers are positive, but it doesn't matter. They could be positive and negative. I don't care. But they're all different. Okay? And there are many pieces of paper. Okay? And he writes a number on each piece of paper and he puts it in a box. And the game is that you have to figure out what the biggest number is. You have to find the biggest number. Okay, now this is these are the rules. They're very simple. You pick the piece of paper out of the box, okay, and you open it up and you read the number. And now you have two possibilities. You can say, I think this is the biggest number. And if you're right, you win. And if you're wrong, you lose the game.
Okay.
Okay? However, if you're right, if you say, I don't think this is the biggest number, and if, again, you're wrong because it was the biggest number, you lose the game right away. If you say anything wrong, you lose the game. You don't get a second chance. But if you say, I don't think this is the biggest number, that's a correct statement. So you're allowed to proceed. So then you pick another piece of paper out of the box. Okay? Another piece of paper, you look at it, and you, once again, you say, now I think this is the biggest number. If you're right, you win. If you're wrong, you lose. But if you say, I still don't think this is the biggest number, then you can play again. If you're right. If it was the biggest number, you lose. Okay, now the question, do you understand the rules? It's very simple. So the question is, what if there were 100 pieces of paper in the box? What do you think your chances are of winning this game? So you would look at a bunch of pieces of paper, and eventually you would get more and more nervous. And eventually you would say, well, I think maybe this is finally the biggest piece of paper, and you guess. So what do you think the chances are of winning the game?
Well, of course, it depends on your strategy.
Well, that's right. You're right. There is a strategy. And the question is, what is the strategy? And, the numbers don't have to be regular. They're not like in order, 1, 2, 3, 4, 5. There's one number is 1.6 and the other one is pi. The other one is 3,000 and 48 million and so on. So there's no regularity in these numbers.
I would say that if I was going to give a solution without thinking too much about it, I would say you probably want to turn over a certain number of cards to a certain point, and then the next biggest one that you find, it'll be something like this.
Right.
But I don't know where that point would be though.
Okay. So that's absolutely correct. You're absolutely right. There is a strategy. It's so simple. I mean, it's almost trivial. Of course, we use this process all the time. How do you find the person that you're going to marry? Okay. You date somebody. You say, nah. You date another person. You say, nah. You date another person. Nah. Eventually you come to a person who's better than all the previous people, and you say, this is the one for me. Now,
it's the best I'll do.
Well, you could be wrong, because if you intended to date 100 people, you might have picked a person who was like number 10 in the list, and you didn't get the best person. So the question is, if you were going to date 100 people, how many people should you date before you decide to take the next better one that comes along? And what's your chance of, in the end, the question really is, what is the chance of winning the game? So would you give me 1 out of 3 odds that I can find the best person in 100?
Probably not. but I imagine I'm going to be proven wrong.
Well, okay, let's make it a harder game. What if there were 1 million numbers in the box? You were going to date 1 million people before you decide. What's your chance of finding the best one in that 1 million? Would you say that? Would you give me 1 in 1,000 that I might get the best person in 1 million? Or would you say I have a better or worse chance? I mean, that's the question.
Yeah. So let's say we start with one box, one piece of paper in the first problem. Right. So it does depend on the number of pieces of paper to a certain extent, right?
It does.
But
to an extent, it does.
But I don't think I'm going to be able to work this out on camera. So
no, don't even try. What is amazing is that this is a way of defining a transcendental number. Okay, so a very, very famous transcendental number is E. Okay, E numerically is a little bit smaller than 3. It's 2.718281828 something, it goes on. So it's roughly 2.7. Okay. So 1 over 2.7 is about 37%, 0.37. Okay. So now I'm going to tell you the strategy for winning the game. You should date 30% of all of the girls that you intend to date, or boys, whatever you, okay? And don't choose any of them. The next bigger one that comes along is what you pick. So that to optimize your strategy, you should look at 37% of all of the numbers. And your chance of then winning the game will be 37%.
37%?
No, 37%. Again.
But shouldn't it be the percentage of... No?
No, it's not. And that's... I mean, this is a mathematical calculation that I can show you. It's pretty easy, but it involves Taylor series. But the point here is, it doesn't matter how many numbers there are. There can be 1 billion numbers. But what you do is your strategy is to look at 37% of 1 billion, which is 370 million. So you look at the first 370 million numbers and you say, no, this is not the biggest number, no. And you keep saying that 370 million times. Now, of course, you could be wrong, in which case you'll lose the game. Okay? But you may be right. And then your objective is to take the next bigger number that comes along. No, I mean, it could be, of course, that the next bigger number that comes along is not the biggest number, in which case, once again, you'll lose the game. But the chance of you winning the game is also 37%. So it's better than 1 out of 3. And if you don't believe me, you can try it at home. Take 27 numbers, different numbers, have your friend write it on 27 different pieces of paper, pick the first 10, say no 10 times, and take the next bigger one that comes along, and you could make if you do this over and over and over again, you'll see that that your history, your probability of winning the game is 37%, which is extraordinary, right? So 37% of 27 is about 10. So you look at 10 numbers and then you take the next bigger one, and better than 1 out of 3 times, you will win the game with that strategy. Okay. And as far as anybody knows, that's the optimal strategy. That's the best possible strategy you can use. So you won't always win, but you win more than 1 out of 3 times, no matter how many numbers there are. That is beautiful. And it's not beautiful. It's not the argument so much. This is different from the other example I gave you. It's that the answer is beautiful because it's amazing, because it's so counterintuitive. Who would have thought that, who could possibly have imagined that your chance of winning the game, it doesn't make any difference how many numbers there are. Your chance of winning the game is better if there are many numbers, of course. So it is very, very slightly, as you pointed out, dependent on the number of numbers, because if there's only one, the chance is 100%. But as you get more and more numbers, it drops down to 1 over E, or 37%.
So for anyone out there who is on the dating scene and they think they're going to be dating from, say, 20 through to 40, those are the years they have available, and they date, say, one person a year, then after 8 years of being frivolous with their dates, they should then settle down for the next best person.
Pick
so from
the next person who's better than everything before, everything that came before. The problem is there may not be. It may be that you've passed your optimal mate. And that's entirely, the chance of screwing this up or choosing too early. That is, you might pick the next better one that comes along, but there's an even better one.
So let's finish
but that's a very
on
powerful strategy, don't you think? That's beautiful.
I think that's, as you said at the beginning, this is what people actually do to a certain extent, right? They date around when they're young, and then at some point they do settle down when they're, I guess, I don't know what the average is, average marriage age, it might be about 30. So it is probably, that sounds about right, actually.
Right. But the divorce rate is roughly 50%. Roughly.
So both numbers work out.
Yeah, I mean, they're pretty close, right? I mean, if you just say, this is the one for me. Okay. Of course, that person may look at you and say, well, you're not the one for me.
But of course, you could have numbers that are very close together. So the next best number might not be so bad.
Right. That's right. And that's the human feature. I mean, there may be lots of people who in the end would be a perfect mate, or not a perfect mate, but an excellent mate. And maybe we could define an excellent marriage as one that doesn't end in divorce. Now that may not be the right way to define a good marriage. I mean, it may not be a happy one. So, but the chance of a happy marriage is not zero. So you date a bunch of people, and then you take the next better one that comes along, and that's the strategy that people basically tend to use. Sometimes they circle back to, you have that option. In this game, you don't have the option of circling back. Maybe the fact that that the divorce rate is 50%, not 67% or something, is the fact that people are allowed to circle back after they realize that they're screwing up and they missed out. And then sometimes you can fix the problem, right?
So let's end on, this is sort of like it's sort of a combined question, but I'll put sort of the combination of questions together. In 1900, Hilbert came up with his famous Hilbert problems. There are these 23, some say 24 Hilbert problems, depending on how you count.
Right. This is an important. I would say just right away, this is a crucial turning point in the development of mathematics, because by doing this, what he essentially did was to split the field of mathematics into two fields. What he said was that mathematics is beautiful, and that we solve problems in mathematics not because they're going to be useful, but because they're just beautiful. Okay, and there's a very elaborate way of defining beauty, as we know, but he said mathematics certainly doesn't have to be useful. So if you want to know how many 6-dimensional balls, what is the optimal number, the maximum number of 6-dimensional spheres that will fit into a 6-dimensional box, you might say, who cares? And furthermore, even if I knew the answer, I couldn't test it in the laboratory. Okay, that's how a physicist would respond. But more importantly, it wasn't important if mathematics could be used by other branches of science. So the mathematics community, 2/3 of that community followed Hilbert and said it doesn't have to be useful. It doesn't have to be applicable. Roughly 1/3, or at least that's what the count is today, have stayed in with the point of view that it has to be useful, it has to be relevant, meaning it can be built on and eventually have a connection with reality, because we do know that the physical world obeys mathematics. Okay, it really does. It really seems to. Okay, so these mathematicians are now called applied mathematicians, and Hilbert's mathematicians became pure mathematicians, and mathematicians didn't have that distinction. It was just mathematics. Okay, I am definitely of the 1/3 variety. And so to me, mathematics is a tool, and it is a lot of fun, and it's beautiful, but ultimately it should be useful. So, for example, one of my expertise, in mathematics, is the idea that although almost all equations are impossible to solve, you have to learn what the answer is like. What are the properties of the answer, even if you can't solve the problem exactly? So you have to learn how to do approximate mathematics. And approximate mathematics, again, is something that requires great care, but not rigor. And that's what I do. Okay, and that's the kind of mathematics that's relevant in physics, because if you encounter a new physics problem, you can't solve it. There's no chance that you're going to find the answer to a physics problem. I mean, essentially all of the problems that you can solve exactly have been solved. And they all involve systems that are too simple to be realistic. Okay, so life is complicated. How do you predict the weather? Well, you can't predict the weather exactly, but the question is, what is the best approximation that you can make? And probably there's an upper bound. You can't give better maybe than a 80% accurate approximation if you want the weather 2 days from now. But how do you get the optimal approximation? Okay, this is applied mathematics, and that is what I love to do. I love to be able to solve a problem approximately and understand what the answer is like to a high degree of approximation without solving the problem exactly.
If you had to pick your Hilbert problems, what would you choose?
I could make up problems, but they wouldn't really be of interest to me. They just wouldn't. I mean, an example.
Oh, I meant for physics. I meant the ones you're interested in.
In physics.
I mean, your Hilbert problems.
Hilbert problems in physics. I don't think there are any.
No, I mean your version. So Hilbert gave his 23 that he thought that were the most important for mathematics, to him personally. I mean, if you had to pick, you had your pick, and you're now going to influence you're going to split the field of physics, you're going to influence the future of the field. You don't have to pick 23, but there might be one or two that you think are particularly close to your heart.
Well, there's certainly a bunch of problems that I would love to see answered. One of them has to do with the acceleration and the expansion of the universe. The reason that I think this is such an interesting problem is that it may be an example of a problem where PT symmetry comes into play. Okay. And the point is that, this goes under the heading of alternative theories of gravity. Okay, because we know that gravity is attractive. Okay, but the universe is expanding and accelerating. So isn't gravity pulling back on it and stopping it from accelerating? And the answer is that, not the answer, sorry, be very careful. Not the answer, but a possible answer is that, in electrodynamics, a positive and a negative charge attract. And they attract just as if they were attracting gravitationally. They both have a 1/r force, okay, or 1/r potential, okay, 1/r squared Newtonian force, okay, and a positive and negative charge attract. But you can make a PT symmetric theoretical model of electrodynamics, okay, where the electric charge is not a real number, but it's an imaginary number. Okay, but everything else is the same. And now you can ask what happens. Well, what you find is that a positive and negative charge repel. Okay, so one interesting possibility is that gravity at short distances, where short means on the scale of a galaxy, at short distances, way out at galactic scales, gravity is attractive. But on the scale of the universe, on very large scales, gravity is repulsive. So you can imagine a theory of gravity, which is where two masses attract. And all you need to do is to look at this theory in the complex plane, and now two masses repel. And if we have a bridge over distances shorter than some characteristic distance, gravity is attractive, but larger than this characteristic distance, it's repulsive, then we can understand something about the structure of the universe. And I think this is an example of a very hard but very interesting problem.
And so the idea is that PT symmetry is then broken at short distance scales and then not at long scales, or?
Righto.
Okay.
That's exactly right. So if you imagine that you begin with a universe that is PT symmetric, but it has a broken PT symmetry, that is, it has the symmetry, but it's like the water pails that are not connected with a pipe. Okay, it's PT symmetric, but it's still not in equilibrium because one pot is filling up and the other one is emptying out. So that has broken PT symmetry. But if you connect it with a pipe, it's unbroken PT symmetry. So therefore, you imagine the universe at great distances being somehow connected by a pipe, sort of. Okay. Well, we can imagine it being broken or unbroken, but the point here is that depending on the separation, it either is repulsive or it's attractive, and there is some changeover distance. So that's the idea. That would be an example of a beautiful, wonderful problem. If you could solve it, of course, it seems to me you would deserve a Nobel Prize. And that's a very, that would be a beautiful, application of the ideas of PT symmetry. Okay, and use of the complex world to understand what is going on.
This is work with Philip Mannheim, is it?
Philip and I have done some work with, of course, with that objective in mind. Philip is very smart, and he's very knowledgeable about ATGs, alternative theories of gravity. He's worked on conformal gravity and so on. In fact, I'm in discussion with a guy in London, where I'm going in a few days, whose name is, he's actually in Greece, but he's coming to London. A guy named Mavromatos, who
I don't know him,
is very knowledgeable about modern physics and gravitation, and we've been talking about this problem for a long time. I mean, this would be a wonderful application of PT symmetry.
Well, Carl, it's been an absolute pleasure having you on the podcast. Thanks for coming along.
Pleasure to chat with you. I had lots of fun.